I wanted to do a little bit harder problem, finding the maximum and minimum values, and I wanted to show you kind of a cool way to find a derivative. First, I'm going to rewrite the original function here as f of x equals square root of x to the fourth multiplied by the square root of 4 minus x. I haven't changed anything. The square root of x to the fourth is x squared. But what I did was create a situation where, because they're both under a square root, I can multiply the x to the fourth in. So now I have the square root of 4x to the fourth minus x to the fifth, which, being as I'm about to find the derivative, it would be easiest, I think, to put that to the 1/2. Let's put the derivative over here on the left. F prime. So put the 1/2 out front. Leave the inside alone. That's to the negative 1/2. Multiply by the derivative of the inside. Okay. Let me rewrite this, cleaning up the algebra, or cleaning it up with some algebra. Okay. 16x cubed minus 5x to the fourth. I'm going to do a little factoring. Knowing that I'm going to need to find critical points, I'm going to do a little factoring on the top and bottom. Okay, so on the top I'm going to pull out an x cubed. The bottom I'm going to pull out an x to the fourth, which I also could pull out then as just an x squared, but I'm not going to do that. Okay. All right. Critical points are what make the derivative 0 or undefined. So let's look at the top to make that 0. Of course, 0 cubed would be 0. And here, if I set this equal to 0, 16/5 would make that parentheses 0. Let me make a note here of those two things. X equals 0. And 16/5 are those critical points. In the denominator, of course, 0 to the fourth and 4 would make the bottom 0. And remember, critical points are where the derivative is 0 or undefined. So plugging in anything, making the bottom 0 makes it undefined. But actually anything over 4 is also a problem, because if we did that, if we put in a number bigger than 4, we'd be getting imaginary numbers. So we're going to need to make note of that. All right, we're going to do sign analysis on this. Okay, so we got 0, 16/5, and 4. 16/5. Of course, this is not to scale because 16/5 is 3.2, but I want to give myself a little room. All right, if I plug in a negative number to my derivative, remember we're doing sign analysis on the derivative. A negative number. Well, negative cubed is negative. 16 minus a negative is positive. So the top, negative times positive, top is negative. The bottom, because it's under a square root, this should always be positive unless it's undefined. And it is defined here, okay, because a negative to the fourth is positive, 4 minus negative is positive. So we have negative divided by positive, which is negative. Now, pick a number between 0 and 16/5, maybe 1. 1 cubed, 16 minus 5, top's positive. Bottom, 1 to the fourth, 4 minus 1. Bottom's positive. Positive divided by positive is positive. Now, let's say we plug in something between 3.2 and 4, maybe like 3.5. Well, 3.5 cubed is positive, but 16 minus 5 times 3.5, this is negative. Positive times negative is negative. On the bottom, this is 3.5 to the fourth, 4 minus 3.5. This is positive. Negative divided by positive is negative. And finally, when I get to 4, I plug in a number bigger than 4. The top is negative, but the bottom doesn't even exist. So what I do is I kind of just black this off, and I say, well, it doesn't even exist over here. Okay? So here, the derivative changed from negative to positive, meaning the function changed from decreasing to increasing. This represents a minimum. Here, the derivative changed from positive to negative, so the function changed from increasing to decreasing. This represents a maximum. Okay? And what we're saying then is I don't even think it exists past 4. Let's pull in the graph so you can see what it looks like. Okay? So here's the original function. You see a minimum at 0, a maximum at a 3.2, and it doesn't exist past 4. So the derivative gives us a lot of ability to analyze some pretty hard functions.